everybody. Welcome to our session, multi-period optimization. I hope you enjoyed PSCC so far. It's an online version. Myself, I really enjoyed so far. We had great sessions, and I'm happy that we have one day more tomorrow, and also a couple of sessions after this session. The topic of this session, as I said, it's multi-period optimization. And we have 6 great papers and 6 speakers to talk about their research. I'm so excited to hear about your work. Just before starting the first presentation, let me give you a few hints. The first is about the Q&A. So while you have any question, even if in the middle of the presentation, you can write your questions in the box below Q&A, and you can write there. And I'll see that, and after the presentation, I'll ask the presenter, I'll ask you a question. That's one thing. And second, I asked our speakers to make sure that their presentation will not exceed 15 minutes. So 1 minute before, I will warn you, and yeah, please be careful about that. Yeah, that's it. So let's start with the first presenter, Christian Naversen from NTNU. Let me give first a couple of, a bio of Christian. Christian finished his master in applied physics from NTNU Norway in 2015, and started working for Sintef Energy Research with short-term hydropower scheduling. And currently he's on leave from Sintef to take a PhD at NTNU, where he looks at the future state of the Nordic electricity and reserve markets from a fundamental modeling perspective. The title of his paper is Hydrothermal Scheduling in Continuous Time Framework. And I believe Christian will present his work live. So Christian, please share your screen, and then you can start presenting your work.
Okay, let's see if this goes well.
Yep.
Let's see. If I put this in slideshow, is everything okay?
Yes. We see your slides and your voice is clear.
Great. Okay, so yeah, thank you for the introduction. So I'm presenting this hydrothermal scheduling in the continuous time framework paper that I wrote together with my co-supervisor, Dr. Arild Helseth at Sintef Energy, and Dr. Bosong and Professor Masood Parvania at Utah University in the US, as well as my supervisor, Professor Hossein Farahmand, and Professor João Catalão here at University of Porto. So I will quickly go through some motivation and background, and also a bit of a basic introduction to the continuous time optimization, and show you some of the modeling we have done, and go through the case description and results. So firstly, my PhD at NTNU is part of a bigger research project called the PRIBAS project, which is funded by the Norwegian Research Council. And the premise here, or at least one of the premises, is that the cost of balancing the Nordic power system will be higher in the future due to more interconnections to the rest of Europe through HVDC lines, and also more valuable renewable energy production in the system. So there's already quite a few HVDC lines connecting Norway in particular to the rest of Europe, and there's also plans for perhaps another line to the UK. And so the question we ask us is, how can the Norwegian cascaded hydropower sort of help provide flexibility to the system as a whole? Because the Norwegian power system is dominated by flexible cascaded hydropower with a lot of storage potential. So it's very tempting to use this for balancing purposes. Yeah, so in this work, we have looked at structural imbalances and tried to model them in sort of a fundamental way. So when I say structural imbalances, I mean this deterministic imbalances created by the structure of the electricity markets. So in the Nordics, the electricity markets are cleared in hourly intervals.
Sorry for interrupting. I think sometimes you get further from your mic. Please be always close to the mic. Thank you. Sorry.
Okay, I'll try. Okay, yeah. So you have these mismatches essentially between the demand and the market clearing schedule. And in sort of a paradoxical way, this can be worsened if you have a lot of flexible production like hydropower, because it is actually more or less able to follow the given hourly schedule because it's very fast at ramping. So then you can have a quite large mismatch, which gives you frequency issues. So we tried to model this by using this continuous time optimization, which is a fairly new thing in power systems, at least. So the main idea or concept here is that instead of assuming a piecewise constant load for each time step, K, like we do here, we assume a piecewise polynomial load. So for each time step now we describe the load as a function of time by using some basis polynomials B here of some degree we choose n. And now we have these coefficients L, J, K for the load in each time interval that describes the shape of the load curve. And these basis polynomials that we use are almost the Bernstein polynomials, which have this shape. And we do this because they have some very nice properties, which essentially allow us to reformulate the whole optimization problems in terms of the coefficients of these polynomials. And the important thing here is that you can actually bound the Bernstein polynomial, so which makes it possible to also implement inequality constraints. And why continuous time? Well, an important thing is that you can apply time linking constraints, which are related to integrals or derivatives directly on the function or variables. So, of course, when you just integrate basis functions, you just get basis functions of a higher degree, and the same when you differentiate. So you can, all of these are just linear transformations, essentially, which means that ramping for thermal generators can be applied directly to the derivative of the production variables to bound those. And also for reservoir volumes or energy content, you can measure the volume increase by integrating the net inflow into the reservoir. So these types of constraints are fairly easily handled in continuous time, and one of the main advantages. Another advantage is that you can have a smooth transition between time intervals, which means that you can say that the production at the end of a time interval has to be the same as the production at the start of the next interval by just equating some of these coefficients, which means that you have now a continuous production curve. And you can also do this to the derivative so that you have a smooth production curve across intervals, which is, of course, the whole point here, because we're looking at these structural imbalances, which have sub-hourly variations, and so we want this kind of behavior. So for the modeling, we have a fairly simple system topology here. We have a hydro area connected to a thermal area with a HVDC line. And in the hydro system, which sort of represents Norway in this case, we have a Norwegian watercourse with well, cascaded reservoir plant pairs connected hydraulically to several different water routes. So it's a fairly sophisticated modeling of the hydropower. Whereas in the thermal area, we have a simpler model with 4 units with ranging from slow ramping and low cost to flexible and expensive. So for the load data that we put into the model, we used data from the US. So in the thermal area, we have this red load curve. And so the smooth curve here is the continuous time curve, which we find by applying a least square error fit to the 5 minutes underlying data we got from California ISO. While the dashed red line represents the hourly average of the same data. So you see this is the famous duck curve from California, which has a lot of ramping down in the morning and ramping back up in the evening as solar power comes on and off. While for the hydro area, we have load from New York. So the modeling here in the thermal system is modeled with sort of the standard continuous time unit commitment constraints and ramping, constant marginal costs. And here we apply these C1 continuous production variable constraints, which means that we have smooth transitions between interval changes. And because we have this smooth smooth operation between interval changes, we need to modify this in the commitment constraints. This is the idea in continuous time that you allow the unit to smoothly start up from 0 and ramp up to above Pmin, which is 20% in this case, within an hour or within an interval. So you allow the thermal units to ramp up their production or equivalently ramp down their production to 0 using a whole time interval. So this is can be a typical production pattern for a thermal unit here. While in the hydropower, we had to do some modeling here we have all the topological constraints for the water balance, as well as I should say we have some cut description or water value description for the opportunity cost of using water. And we also have these linearized production functions that relate the discharge of water through the turbine to production. This is a very nonlinear function, and it is usually linearized in optimization models. But in the continuous time framework, it turns out you actually need some extra binary variables to make this work, because you need to make sure that you use this linearized segments in the right way. So you don't start using segment 2 before segment 1. And a main important thing here is that we allow partially discontinuous production variables, which might seem kind of counterintuitive. So only for the hydropower. So a hydropower unit might operate something like this in our model. The red line is the production curve. So we actually allow it to have discontinuous startup and shutdowns, like in our 14 here. And this is because, as I mentioned earlier, hydropower units actually can almost start up and shut down discontinuously in the real world. Well, at least within some tens of seconds or maybe a few minutes. So we do this, we implemented this in the continuous time model to sort of retain some of the flexibility of the hydropower units, because this very unlikely that anybody will operate a hydropower unit like I showed you for the thermal units. Nobody will actually run a hydropower unit between 0 and Pmin for a whole hour to ramp up. So this might seem like a pretty big relaxation in the model, but actually it is more accurate, I would argue. So when the unit is running, it still has to be continuous, but we also allow it to have...
Christian, sorry for interruption. There is 2 minutes left for you.
Okay. Classified. I'm almost done. Yeah. So finally, we have the transmission system model. So we have a load balance in each area and transmission limits for the AC HVDC line. And yeah, this also forces the sum of hydropower production to actually be smooth and continuous, even though the individual hydropower units can have discontinuous production curves. And of course, we also have an objective, which is just to minimize the total system costs. So when we run the model, we run the continuous time model, and also analogous hourly model, which is what we are all used to, I guess, which is the dashed line here. So you see in the thermal area, in the hourly model, you would actually turn off all the thermal units when the load is ramping down and then turn them all back on in the evening. But this is actually infeasible or extremely costly in the continuous time model. So here you keep the base load running for the whole day actually. And the flow on the line from the thermal area, from the hydropower area to the thermal area looks like this. So for the beginning and end of the day, both models try to export as much power to the thermal area. But you can clearly see that in the continuous time model, you have a smooth ramping down and ramp back up to help ramping problems in the thermal area. Well, the hourly model, you see these two spikes or sharp drops in power flow, which can be sort of problematic for the system operators when it comes to balancing, to have these sharp changes in flow. So to conclude, the discrete time model or the hourly model so overestimates the system flexibility. And in that model, the hydropower mostly provides cheap energy for the system, trying to export as much hydropower to the thermal area. While the continuous time model can sort of capture and realize that the ramping problems are actually quite severe. And so the hydropower provides both cheap energy, but also ramping flexibility. And because the continuous time model load data is a better fit or better approximation to the underlying time-minute data, we get less structural imbalances in the system. So they're reduced by about 34%. And that was it. So I hope I didn't go too much over time.
Yeah, thank you. Thank you so much, Christian. It was very nice work, nice presentation. I see that still there is no question, so maybe I can start while the others are writing their own questions. So it's interesting. So Christian, so compared to discrete model, it sounds that your model is more smoother and doesn't overestimate the system capability, as you said. But what is the computational cost, not just in terms of the CPU time, but also the number of variables, constraints, and also sounds that you are adding some binaries. So can you add some descriptions about computational cost?
Yeah, so definitely you increase both the size of the model in terms of variables and constraints.
By which factor? Is it a factor of 10? Is it a factor of 100?
No, it's about a factor of 4, because you have, for degree 3 basis polynomials as we use, you get 4 coefficients. So you get about 4 times as many variables, but also more constraints. But yeah, and you also get these extra binary variables for the hydropower. And they do increase the computational time quite a lot. Especially, it seems to be harder to find at least the optimal solution. So you can converge quite fast to a decent mid gap, but to get it fully to optimal.
So Christian, you add binaries just in continuous model. In discrete model, we don't need those binaries?
No, you still have some binaries in the discrete time model for the unit commitment decisions, but not for the hydropower production.
So you have more binaries because of the continuous model.
You have some additional binaries.
Okay, very nice, very nice, very nice. Yeah, I see that we are we are yeah, the right time to go for the next one. Christian, it was very nice work, and I really enjoyed it. Thank you so much for this work. Thank you. Let's move on. The next speaker is Luik